Welcome to part 2 of chapter 7, focusing on arrays and lists. So what we're going to talk about now is the enhanced for loop. The normal for loop uses indexes to iterate through items. The advanced for loop is more elegant in that it actually iterates through the items directly. So for example, the old way of doing it, you use a for int I equals 0, I is less than n, etc. Here, what we're basically saying is the equivalent of for each. For each element in the collection values, go through and add total to the total elements. The loop body is executed for each element in the array, and it can be read as for each element in values. This compares to the traditional array element. I think this is much cleaner and easier to read. You can't use this for every array algorithm. Usually for ones you have to modify the array, you can't. For example, you can't use it to modify all the elements in an array. For that, you use a basic for loop. Consider the element in the for each loop as a read-only element. You can't really edit it. If you do not need to index other values, you can use an enhanced for loop. It's a convenient mechanism for traversing all elements in a collection in a clean and easy manner. Here's the syntax. You say for each type name variable in a collection. This variable is set in each loop iteration. It's only defined inside the loop. So if you try using it outside the loop, it's going to blow up on you. Let's talk about some common array algorithms. So here's an example. Fill an array with squares. For int I equals 0, I less than values, go up, and include it for each. The point here is to show that we do a set of operations across each item in the array. Compute the sum of all elements in the array. Basically, we define a total outside, and for each element in the array, we just go through and add it in. Notice we're using an advanced for loop here. To obtain the average, we basically take that result and divide it by the length of the array. Pretty straightforward. Finding the maximum or minimum is pretty straightforward. Go through each element. Grab the first element, say it's the largest. Go through every element. If it's larger, switch it out, and by the time you're done with the array, you'll have the largest element. For minimum, just flip this on its head using less than instead of greater than. One thing to keep in mind is the array here can't be empty, or else you will catch an error. When you display the elements in an array, you usually want to separate them. Notice that there's one fewer separator than there are elements. So what we do, a little bit of coding here to stop the first one from being printed. Otherwise, we print it each time. So how do we find the position? We visit all elements until you have found a match or you have come to the end of the array. For example, find the first elements equal to 100. Search through it. If we find it, found is true, and we can get out of our loop, or you could use a break instead of this. This is primarily used for unsorted arrays. It's called a linear search, and it inspects elements in sequence until a match is found. To search for a specific element, visit the elements and stop when you encounter the match. This has an average performance of n over 2, where n is the number of elements in the array. Removing an element can be a bit of a pain. To remove the element with index pos from the array, we need to overwrite the element with the last element of the array if it's unordered, because we don't care then. So the easiest way to do that is decrement our current size value after overwriting the element. So we say value of pos equals the last element of the array, move it in here, and forget about this guy. However, in an ordered array, it's more of a pain because we have to move everything up. So we move all elements following the element removed to a lower index. Then we reduce the size of the items in the array. So we go from the position we want to move plus 1 here to the end of the array, or the end of used elements, and we move everything up 1, and then we say ignore that last element. Inserting an element. If order doesn't matter, insert it at the end, increase the tracking variable. Easy. If it does matter, we have to do the opposite of what we did for delete. We're going to increment the tracking variable, move all elements after the insertion to a higher index, move this guy down, and so on, and insert the element. Now you got to be careful here, because if you go past the length of the array, you will catch an error. So something to keep in mind. To swap two elements, you need a temporary variable, because you'll erase it if you don't. So save the first variable in a temporary variable, replace it, and then take the new variable and set it to the replacement value. So temp equals the current value of I. Value of I equals the one we want to swap with, and then we set the one we swapped with back to the original. Here's a nice infographic for it. Basically, grab our value, put it in temp, swap it, and then swap it again. Copying an array currently yields a reference to the same array. What we want to do is actually make a copy or a clone. We use the arrays.copyOf method here. So we say double prices equals array.copyOf values value.length. The interesting thing here is you don't have to copy the whole array if you don't want to. However, in order to do this, you need to add the arrays package to the top of your class by using an import statement. So what happens when we run out of space in an array? Well, what we can do is create a new array and use copy into it. So new values equals copy of, and then use a bigger length. Then say values equals new values, because they're both references and they both reference the same bigger array. To read a sequence of an arbitrary length, add the inputs to an array until the end of input's been reached. Grow when needed. So we're going to set an initial size. We're going to grab a number. If we've exceeded our maximum length, we're going to copy it into a larger array. And then we're going to set the value and increment our number of used items. And we can then get rid of unfilled elements by resizing our array to just be the current size. So here's some code to show how to get the largest value in an array. Just running through it rather quickly. So by combining fundamental algorithms, you can solve more complex problems. Compute the final quiz score by dropping the lowest score and finding the sum. Well, calculating the sum, find the minimum value, remove an element. So find the minimum and remove it from the array, then calculate the sum. So we'll need to use a certain linear search to find the position of the minimum. Now, we can revise this a little bit. Find the minimum, find its position, remove that position from the array, and calculate the sum. Here we find the minimum of 4. It occurs at position 5. We're going to remove it, which moves everything down a bit. Then we're going to compute the sum. And this is how this strategy works. Always look to refine your algorithms. It's inefficient to find the minimum and make another pass through the array. So we could modify the algorithm to remember the position of the smallest. So running through, we can find the position of the minimum, remove it from the array, then calculate the sum. So for our first example, we're going to demonstrate counting the number of zeros in an array using an advanced for loop. So we declare our array to have a couple zeros in it, define our counter, then we say for each element in values, if it's 0, add 1 to our counter, and print it out. Pretty straightforward. Next, we're going to modify the print array method I've been using, which runs through each item and prints out each element in an array, basically to use it for advanced for loop. Item in array, and then here we'll just print out item. And we can run this. And boom, there we go.